Hey, so I had a bunch of questions about how I apply formal verification to machine learning and vice versa. So I thought I'd make a video to walk through some of my projects. So I'm going to start with prior proof. This is a way of measuring novelty for a formal proof, so for a lean proof. And what initially motivated this project is that I had this project called GPT Erdos. So I had solved a couple of Erdos problems using ChatGPT, and there was dispute on whether that actually represented an advancement of mathematical capabilities of LLMs. And that's partly because it was unclear whether the proofs were actually novel. So that was our original motivation. But novelty is more than just that. It's a higher order property of proofs. It's kind of like interestingness. There are other higher order properties, which I'll get into. But what's special about novelty is that it's not about just the statement itself. There are some properties like utility or usefulness. You can assess the usefulness of a statement just assuming it's true. There's a bunch of formal definitions to do that. But for novelty, you need to know what the proof actually was. So, for example, a widely considered novel proof is like Euler's proof that there were infinitely many primes. We already knew that that statement was true based on the prime number theorem, but Euler's connecting number theory to analysis in a way that had never been done before. So that proof is considered to be novel. It's about the actual methods that are used. And if you ask a bunch of mathematicians whether a particular proof is novel, there is some disagreement, but for the most part, they tend to agree. So this is something that's real, that's probably worth measuring. And I just wrote some of the use cases of being able to measure novelty here, where the first one is the use case that I had initially envisioned, which is basically just benchmarking, is this LLM actually doing new math? But I think that the reason why there's so much disagreement about novelty is because it's a form of intellectual credit assignment. It's a way of saying, did this person actually deserve the intellectual credit, or does it belong to someone else for the existence of this proof? So that's another reason why it's important to be able to say that a proof is novel or not novel. And the third is that it's sort of a proxy for pedagogical value. When you're looking at a novel proof, then we hope to learn something new about mathematics. It's telling us something that we didn't know before. So those are some of the reasons why we might care about novelty. And I want to propose a concrete definition for it. So these are other higher order properties of proofs that you may or may not be familiar with. Utility is sometimes formalized in this Kolmogorov complexity type analogy, where if you take a new lemma, then its utility is how much it allows you to compress an existing corpus. And of course, there's syntactic compression, which you'd want to ignore, like syntactic sugar. We care more about semantic compression. So there's variations of this. Importance is sometimes captured via the number of proofs that directly or indirectly depend on some lemma. But even that has to be refined a little bit because you'd end up with all infrastructures being the most important lemmas rather than actual proofs. So some kind of filtering is usually applied. There's concepts of identity for proofs. So maybe one proof takes a detour, but semantically it's actually identical to some other proof. So there's ways to normalize proofs and say that they're identical. So my proposed definition for novelty is that it's the surprisal of a proof relative to some prior distribution over proof contents. So that raises the question, what are proof contents? Because there's different ways that you might define that. And I think that a reasonable first approach is to basically create this ontology. And this was my first approach, to try to define what is the core strategy of the proof, what is the existential style, what are all these different properties of the proof. And then you could imagine using like an LLM to classify each of the proofs that's in the corpus or classify an unseen proof. But I think that opens you up to a bunch of disputes about whether the ontology that you defined is actually reasonable, because now the novelty of a statement is a function of that ontology. And people might have disputes about whether a proof was actually correctly classified within the ontology. And there's just a bunch of human subjective elements that come into play if you approach it this way. So instead, the way that I approach it is I use the dependencies of the lean proof, because we're working on formal proofs. So we know exactly what other lemmas are being invoked. And that allows us to have some consistent canonical way of comparing proofs. But then the question is, what dependencies are actually fair to include in the distribution? Because if you just have some filler dependency, like in this case, we have proof A, which invokes lemma B, And then you have proof A prime, which is proving the same statement. It invokes lemma B prime, which is really just a cover, a thin layer on top of lemma B. So proof A and proof A prime should basically have the same novelty rating. There's no reason to believe that one of these proofs is more novel than the other, just because of this filler lemma, which might even just be syntactic sugar. So the way that I solve that is I define some concept of established machinery. And what it's saying is if something is directly or indirectly invoked some threshold number of times, so I'm highlighting k equals 3 here, then we consider it established. So here, lemma 3 is directly and indirectly invoked by lemma 5 and 7. So this is only 2 dependencies, so or 2 references. So as a result, this is not established. But lemma 1, for example, is depended on by lemmas 4, 6, and 7. Lemma 2 has a bunch of dependencies. Lemma 8 has 9, 10, and 11. So these are the established machinery in this diagram. And the place where I actually specify that logic in the code is here. So it's under this families.py file. And it's a little bit more complicated because let's say a dependency itself is not considered established, then I look at its namespace. And if that's not established, then I look at its namespace's parent, then its module, and so forth. So here you can see if we're iterating over some proof's dependencies, then we basically select the first element out of this list that has sufficient support. So that's the way that this works. And now the second question is, so given a proof, we're able to extract what are its established machinery, but what does the prior distribution look like? What should we expect that machinery to look like? And that's what this is solving. And if you want to have any kind of distribution of machinery, then there must be some existing corpus of proofs that we're looking at. So I pick mathlib, and I basically just pick a commit, so some specific point in time. And from there, you could, in theory, just have some prior distribution that you define over this entire corpus. So this is just a very simple summary of how that system might look. You have your mathlib corpus, you construct some distribution over those established machinery that we previously defined. And then finally, you have some novelty function where it takes an unseen proof that was after this dependency distribution was constructed, and it just computes the surprisal of the distribution of established machinery in this proof relative to the overall distribution. But what that fails to capture is that the distribution really should depend on the lemma, because some machinery that's considered standard in algebraic geometry might be considered unusual in analytic number theory. So the actual area of math matters, and we need some way of selecting some neighbors of the lemma to have some valid distribution to compare against. So one way that you might think to collect those neighbors is just by constructing a DAG of dependencies across all of the lemmas, and then you would sample the neighbors from there. But that's sort of circular because in the case of a novel proof, we're basically saying that those dependencies are going to be very unusual. So its neighbors, based on its dependencies, are not going to be an accurate representation of proofs that we would expect to be similar. So instead, the way that I solve it is I train this embedding model. And I just take mini-LM and I take its embedding model and I train it through contrastive fine-tuning. So that's what I'm basically doing in this part where this is the actual encoding. And you can see that we're using record.statement. So this is just the pretty printed statement. It's not using the actual proof itself because we don't want to contaminate our embedding with the proof contents itself, because then it's going to look for statements that have similar proofs. And that's not what we really want. We really just care about the statement itself. And this is where we construct pairs that are used for the contrastive fine-tuning. So this is the relevant folder for that. And that's a high level on how this whole thing works. I think that I had another file pulled up here. Yeah, so this is just the pipeline of how it all comes together. But right now I'm in the process of getting human ratings for the proof, the novelty of a bunch of different proofs. And I'm going to compare the system's ratings to those human ratings. So the hope is that the amount of variance between the system versus a randomly selected human is around the same as as the error between two randomly selected humans. So that's what I'm trying to find. And I think it's also worth checking that embedding model and making sure that the lemmas that it considers to be similar actually are indeed similar. So those are a couple of things that I want to get check. And I feel like the embedding model is the place where I feel the most skepticism, just given that the prior on many LM's embedding model on assessing the similarity of lemmas is basically noise. Like there's not going to be any meaningful prior there. So getting that fine tuning right, I think will matter quite a bit for having a reasonable prior distribution to compare against. So that's where this project is heading. There are other directions that I'm interested in related to higher order proofs or higher order properties of proofs. So, for example, for lemma selection, some of these proof systems will compose a bunch of lemmas and produce intermediate lemmas on their way to proving a target. And selecting the right intermediate lemmas to prove is very important. And I think another reason why it's important to know which lemmas to select to prove is because in the future, I think we'll just have extra compute sitting around in the same way that we have AWS Lambda for burst compute or whatever extra capacity sitting around when processors are not at 100% utilization. And I think that one meaningful way to select net lemmas is by using the utility of a statement or the expected utility based on some sort of model. And maybe you can use compressibility as the metric for that. So that's one direction that I'm interested in. But anyway, so here's a link to the repo. I have my email here. I'll try to make another video on verifiable transformers, which is another project where I apply formal verification to interpretability. And I try to prove useful properties of a transformer variant using an SMT prover. So that's the video that I hope to make next, but feel free to reach out to me if you have any further questions.